I think just to clarify on that last question, were you asking for the actual values or how to calculate LP and LR? Yeah, why it's LP and LR. That's what I've always called them. But they do exist. They can be calculated. You end up having to get more numbers. And actually, I'll show you. I'll reference a table for them, but you'll see in a minute that it's just a lot easier to do all this using the beam charts or tables. Okay, in those design equations that we looked at, there was if you derive those formula, you assume that you have a constant moment diagram, meaning that the moment is the same or constant all the way across the length of the beam or along that unbraced length. The problem with that is that very rarely occurs, but this is the worst case because what it does is it puts the maximum stress in the compression flange along its whole length. So it's like having a column that's fully stressed. But in reality, you very rarely get that, so you need an adjustment factor. That adjustment factor is called C sub B. It's the moment correction factor. But that, if you go back a page, you note that it shows up in those formula. And what you do is you end up getting a value that may be greater than 1, and so it ends up increasing your design capacity when you put it in. You got to watch out in using this. On this page and this page, I give you, if you want to go through, you can figure out how to use it. But what I've seen, and you'll see this in the design examples that we sent up to you in those books, that it's conservative just to use C sub B equal to 1. Okay, and the reason for that is you're not going in with a C sub B greater than 1, which would increase your moment capacity. So you're assuming that you got less strength than you actually have. For the purposes of this exam, that's what you want to do because they won't count you off for that, but it will save you a lot of hassle and time in trying to calculate some value other than C sub B. So I'm not really going to go over this in great detail. Probably just cost you points if I did. In the design manual, they have these beam charts, and what these actually are the plotted design equations for all the beam sections. And you look at this and you say, you know, what is going on? Okay, but if you look a little deeper into this, you'll find that it makes some sense. And what's happening is for each section, say here it's a W12 by 35, they're going through those design equations and plugging in for successive values of L sub B, the unbraced length, and plotting the point out. And what we're plotting is B M sub N, or the moment capacity, versus, and it's cut off here, versus the unbraced length. So what it allows you to do is go in with your unbraced length and your design capacity. You'll come in with an intersection point, and what you have to do is pick a section whose line or curve is above and to the right that intersection point. And the problem with what I've done here is I've cut off the bottom scale, so I'm not sure what the unbraced length is. But say we come in and let me pick out one that will explain my purpose, let's say we've got a moment capacity occurring in our beam of 120 kip feet. Okay, and our unbraced length is, I believe that is 10 feet.
We'll just count how many little squares is that?
Yeah, but it doesn't always start at 0.
Yeah.
Let's say...
Do they have the same picture you have?
I don't know. But let's say it's 10 feet. You come in, you need 120 kip feet and unbraced length of 10 feet. That's your intersection point. Now, in order to pick or select a beam that has adequate capacity, you've got to go to the right and up. And as you come up, you come to this dashed line, and if you follow it up or down, you find that that's a W10 by 39. And that one will work, but it's dashed. And it's dashed because it means that if you keep going up, eventually you'll come to a solid line, and that solid line also works, but it happens to be lighter in weight, so it's more economical. So you keep going, and the next one, it's another dashed line. It's a W12 by 35 if you follow it up. That will work, but the first solid line, hopefully you got the same curve, same set of curves. I think I copied them correctly. That one is a W14 by 34. Okay, and note that that's less than the W12 by 35 in weight, as well as the W10 by 39. The second set of numbers after the X in the designation of the section is the weight per foot per length of beam.
So you got the 10 feet from the distance between the braces?
Now this would be given in the problem. The unbraced length L sub B would be given. It'd be the bracing between, it'd be the length between bracing points, as you'll see in an example problem that's coming up.
And then you got the phi m sub n. That's off the moment diagram.
That would come from the moment diagram. Okay, looking at these beam charts, there are a couple important observations. One is that the beam charts are for C sub B equal to 1. Again, for the purposes of this exam, always assume you have C sub B equal to 1. Unless they ask you to calculate C sub B or something, but they usually don't. Again, it's conservative and it saves a lot of time. The horizontal portion of the curve, if you go back, you notice that each curve eventually plateaus out. That defines the maximum moment capacity of the beam section. That's phi m sub p. If you follow the plateau, eventually you come to a solid dot. That defines the limit of the moment capacity as defined by phi m sub p, and that also gives you L sub p. After that, as the unbraced length increases, or as you keep going right, you begin to go down a slope. And that's you keep going down until you hit an open circle, and that defines L sub r. Okay, there's that L sub r again. And then beyond that, you actually get a curve. Between the solid and the open dot or circle, it's a straight line, linear line. Again, a solid curve or line represents the lightest and hence the most economical section. A dashed curve or line indicates a lighter section with equivalent or larger moment capacity exists if you just move up a little bit. Now, if you're designing for economy, that's fine, but watch out. Sometimes when you go and you pick the lightest section, you may end up with a beam section that has problems with deflection. And that's something else we have to check, which we'll do in a minute. Okay, designing with the beam charts, what you do is you calculate your design moment. That's from your loading. It's factored Again, that comes from your moment diagram. You say, well, okay, that has to equal my design capacity. So you go in with your design capacity and your unbraced length. You find that intersection point, and again, you just find the first solid curve or line above that intersection point for the most economical cross-section. Actually, this should be when L sub B is greater than 1. C sub B is greater than 1. Again, I'm telling you, just go and assume it's always 1. It'll make life a lot simpler. And for the purposes of this exam, forget about this. I probably shouldn't have put it in there. If you want, again, you can do the whole design using those beam curves. There are also these, what they call load factor design section tables that give you the values for L sub P, L sub R, and phi M sub P, and then this other term, phi M sub R. And they're, I think somewhere I give you page numbers to these tables. And again, you can see these values. But again, you can pick everything out of the curves. Did you show them?
Yeah, Did you show them?
Okay, as a example, let's say we've got this simply supported beam, uniformly loaded with a service load or unfactored loaded dead load of 2 kips per foot and a unfactored live load of 3 kips per foot. We're going to use A36 steel, and we're going to assume that lateral bracing is only at the end supports. Supports will always give you some type of bracing, lateral bracing against lateral torsional buckling. But now we only got lateral supports at the end, so now what happens is the full length of the beam is equal to L sub B, or L sub B is equal to 20 feet. First thing you do is calculate your moment, maximum moment due to your factored loading, so you factor up the service or unfactored load, so it's 1.2 times 2 kips, 1.6 times 3 comes out to be 7.2 kips per foot. Use that to calculate the maximum moment, which for a uniformly loaded, simply supported beam, it's WL squared over 8. Again, that's something you should have memorized or tattooed on your brain, that formula. And that comes out to be 360 kip feet. I do this intermediate calculation here, which you need to do if you're going in with a C sub B greater than 1. Okay, if you feel daring. But if C sub B equal to 1, you can pretty much ignore that. Again, assume C sub B is equal to 1. You go into the beam charts, so you're entering the beam charts with a phi M sub N equal 360 kip feet and L sub B of 20 feet. That'll give you an intersection point, and you find that the lightest W18 is a W18 by 76. Okay, unless you have the manual, I don't give you that portion of the beam curves that this occurs on. Okay, any questions on that?
So again, you just entered L sub B down at the bottom, 360 over on the left-hand side, found a page where those numbers are, and you just put a point and found the first curve.
If we drew those beam charts, it would be LB, phi M sub N. So we're finding where we have 360, and we look where 20 feet is, and we just go up, find that intersection point, and find the first solid curve, and it's a W18 by 76.
That's the first solid one.
First solid one. There may be, I can't remember, but there may be some dashed lines.
But they're not the lightest.
No, actually, no, that's wrong, because it's the first, so if you're asked for a given depth of beam, that's what it is.
Okay. So in other words, you may have had to skip a couple of solid lines to get to the lightest 18.
18, yeah. Because the next, if you're told to pick a certain depth, and again, the depth is given by the first number in the designation, you can't get a dash line, go up and get a solid line that's lighter in the same depth cross-section.
Okay.
Hope that didn't confuse you more than it helped you. If we go back and say, well, what if we have a bracing point at midspan? What that does is it gives you a new unbraced length of 10 feet. Now, if you conservatively assume, again, that L sub B is equal to 1, now what you do is going back in, instead of going in with 20 feet, you go in with 10 feet. You're still going in with the same design moment, but now you can probably pick up a lighter W18, and in fact, in this case, it's a W18 by 71. Okay, using the correct value of C sub B, turns out that you end up with the same thing anyways, and I'm telling you, forget all that. It's just easier to be conservative and use C sub B equal to 1. In shear, again, typically what happens is we select the beam based on flexure and just check it for shear. The shear capacity is in a W shape. It comes from mainly the web. What we do is we look at the area of the web, and it's defined as the full depth of the cross-section times the thickness of the web. And so D times T sub W is the area of the web, times the strength of the shear capacity is going to be that area times the stress, the maximum stress that can develop over that area, and for shear it's Fy times that 0.6. Okay, don't forget that, times 0.9 for a phi or a reduction factor. Okay, these values, you don't have to do this calculation. They're all given to you in tables, and I've referenced the page numbers for those tables. Okay, but typically you don't have a problem with shear unless you have a short span and or if you have a concentrated load near a support. Watch out. If they give you a problem where a large concentrated load is like 2-3 feet off the support, watch out because shear may control. If we go back to the second, the section that we choose, that we ended up picking for the previous example, that W18 by 71, let's check it for shear. On the loading, based on that factored loading, distributed loading is 7.2. The shear it's WL over 2, so it's 7.2 times 20 feet divided by 2 for a design shear that we need to resist is 72 kips. The shear capacity, running through the numbers using the section properties, comes out to be 178 kips, so we're okay. Don't have a problem. If we use the tabular value, which happens to be on page 4-50, it also gives us the same thing, which it should, because that's how they get those numbers. Deflections, the problem with LRFD is it really doesn't give you any guidelines for deflections. It just tells you deformations in a structural member or structural elements due to service loads shall not impair the serviceability of the structure. Okay, with deflections we check, or when we check deflections, we do the calculation of the deflections, which you should have covered in a previous section, but we do it on the service loads. Okay, because the theory behind there is we don't really care how much deflection we get in our floor beams when the world is coming to an end. Okay, what we don't want to happen is the floor to vibrate or deflect excessively when we're using that building under normal use. Okay, so don't factor up the loads to do that calculation. You know, if you went out to the the naval base that was out at Subic Bay at near Mount Pinatubo, I can guarantee you they couldn't care less how much their deflection they got in their floor beams when that volcano and the earthquake and the typhoon were occurring at the same time. For deflection criteria, you have to really dig back to the older specifications. They say that the deflection you get due to live load should not be any greater than this ratio here, where L is the span length and divided by 360, and make sure that L is in inches to get consistent units. We only check live load because dead load usually can be taken care of by putting a camber or reverse curve in the beam at manufacturing or fabrication, or when they pour the concrete slab, it usually deflects and the concrete fills up that slight depression. Going back to the W18 by 71 that we looked at previously, doing the check for deflection, the live load due to the service load, which is here, it's 3 kips per foot. But watch out, you got to convert everything into inches for consistent units, so you divide that by 12 inches per foot. The total deflection due to the live load, service load, unfactored, is about 1/3 of an inch. Using L over 360, then again, getting the length into inches, is about 2/3 of an inch, so we're okay. Now we're only 50% of the maximum allowed, so the W18 by 71 works. Okay, we also have to be concerned of what happens at supports, and if we have, or if our beam is subject to a concentrated load. That concentrated load may cause a very high stress locally. To prevent failure from that high stress or load, we use a bearing plate, and we need to size the bearing plate sufficient in length such that it kind of evens out that stress or spreads out that load. The failures that we can get here are local web yielding or web crippling, and the design criteria is given in Chapter K of the specifications. Web yielding, what happens is that you actually yield the steel right underneath the load in the web. Crippling, what happens is the web plate just buckles on you. And for local web yielding, if you go into Chapter K, then it gives you 2 design formula depending upon whether you're at the end of the beam or you're a distance D away from the end of the beam. And essentially what you're actually calculating is the resistance that you get in the web. These design equations have in them N, which is the bearing length, so a lot of times what you're doing is you're letting your reaction equal the phi r sub n, and then turning things around and solving for the required length. What happens is the strength goes down at the end of the member because the stress at the end of the member can only spread out in one direction. We assume that it spreads out at a slope of 1 to 2.5. Okay, at the end it can't spread out in both directions, so the strength is lower as opposed to being out here. That shows up in the calculations here. If you go into the uniform load tables that I previously referenced, at the bottom it gives you values of R1 and R2 that can be used, that actually do the computations in here for the various beam sections, and all you have to do is plug in a value of n, whatever it is. They also give you this phi r without any subscript, and that's assuming a bearing length of 3 1/4 inches. I have no idea how they came up with 3 1/4 inches.
Is that kind of a standard plate to put under there?
I guess it's a standard plate size. It used to be 3 1/2, so they've cut it down. If you go into Walmart and ask for a bearing plate, that's what they'll give you.
Standards.
Web crippling, the equations are a little more involved, too involved to get into in this, for this exam. Again, rely on the simplification that's given at the bottom of the load tables, this R3 and R4. All you got to do then to come up with the strength is plug in your bearing length. Going back to the W18 by 71, again, what we've got to do is make sure we can resist the reaction. The reaction we said was 72 kips. It was also equal to maximum shear force. Using the table on page 4-50, we can come up with the R1 and R2 for web yielding. We'll assume that our bearing length is 3 inches. You know, that's given. We come up with 120, and that's greater than 72 kips, so we're okay. Likewise, for web crippling, using the tabulated values of R3 and R4, plugging in our 3 inches, we come up with 118, and that's also greater than 72 kips, so 3 inches would work. We go back and maybe try 2 inches and see if that would work. Probably not, but maybe 2 1/2 would work. Okay, we've kind of looked at a beam, a column, and a tension member. What happens in reality is that you kind of get combined loading. You may have a column that also sees bending. So what you have to do is proportion the member to resist those two forces. Okay, and this type of problem comes up a lot on these exams because it draws in your knowledge from various areas of steel design. The combined loading, it could be biaxial bending. We may have axial tension with bending or axial compression, a column with bending, and that's called a beam column. We evaluate the strength of the member under the combined loading by using an interaction equation, or interaction equations, and they all have the same form, where what we do is we look at the ratio of the load effect to the design strength for each load that's occurring in the member and make sure that the summation of those ratios comes up less than 1. If it's less than 1, then we have adequate capacity in the member. If it exceeds it, it's saying that under the combined action of those loads, you're using up all the capacity of the member and more. You need a larger member. In biaxial bending, where we're bending, this has been idealized, but where we're bending the member about both axes, what we have to do, again, is use an interaction equation. We'll take the design moment. Again, this comes from the loading or your moment diagram. You put that for both axes in the numerator, and then divide that by the strength, and put that in the denominator, where the strength is for each axis, where the strength in the x-axis may be equal to the plastic moment, or phi m sub p x, but it may be reduced by lateral torsional buckling. Okay, so you'd have to go back to the beam charts to find that and put it in here. The weak axis, it's always based on phi m sub p. There's no problem or no lateral torsional buckling when you bend the beam about the weak axis, because it's not going to buckle into the strong axis. There's enough resistance there by the strong axis bending to the member to prevent that. Okay, so remember that the numerator is due to your loading and the denominator is due to the capacity of the member. And again, this has to be less than 1 for a safe design. Just doing a quick example where we're saying, I've got this W18 by 50, we use A36 steel, and given, due to the loading, we've got a moment diagram for the x-axis that gives us a maximum value of 100 kip feet, and at the same location in the weak axis, we have 20 kip feet. So these are all given. To evaluate it, what we do again is take the loading, put it in the numerator. Here we're converting the moments into kip inches, so the units are consistent. The moment capacities for both axes, we're assuming that there's no LTB. We're basing everything on the Z, ZX, and ZY. Again, it's a simple calculation. Coming and running the numbers, we find that we're only up to 81% capacity of the beam, so we're okay. So that member's adequate. If we came over 1, what would happen is we'd have to go pick a larger section. Okay, axial tension and bending. Now what we have to do is design the member not only for bending but as a tension member. So what we do is we calculate capacities as a tension member. We end up with 2 interaction equations, and which one we use is determined by the ratio of the axial load, axial tensile load, to the axial tensile strength. And again, that's a tension member. If it's greater than or equal to 0.2, we use this one. Less than, it's this one. And so again, what you got to do in order to get this value here, you got to consider all possible failure states for a tension member. Gross section yielding, net section fracture, and block shear. And again, they like to put combined loading on these problems because it gets you involved into very many aspects of steel design. It's one member, but you got to treat it as a tension member and also as a bending member. The most difficult combined loading case is when you have axial compression and bending, or a beam column. The problem there is as the member deflects due to the bending from the transverse loads, the axial compressive force becomes eccentric, and you end up with an additional moment. Okay, it's a second, what we call second order effect, or a P delta effect, and the beam deflects a little more because of that. And what we get, or what we say we get, is a moment magnification due to this P delta effect. So what we're going to have to do is throw another factor into the equations. And this moment magnification factor for brace frames, it gets more complicated when it's unbraced. There's actually another moment magnification factor. Don't worry about it because typically they don't go into that complexity in these problems. But the moment magnification factor is B1, and it's given by this term here, where PE1 is the actually Euler buckling load, where you're actually using lambda sub c for the member. That's easy to calculate. The C sub m is similar to the C sub b term that we used for bending capacity, but likewise, I told you for bending capacity for C sub b, use C sub b equal to 1. It's conservative. Here, the same thing. Just use C sub m equal to 1. It saves you a lot of hassle. The code or specification does give you values more exact values for C sub m, but it's not worth the effort on an exam like this. Okay, what this will do is give you a value that comes up greater than or equal to 1. And in a sense, what it does is it multiplies your moment, and so it gives you a larger moment, and that takes into account that extra moment from the eccentricity caused by the axial compressive load. The interaction equation then is given by the following. It's similar for what we had for axial tension and bending, but now the strength that we're going in with is for a column. And again, this is the bending strength may involve lateral torsional buckling, and the only addition then is the moment magnification factor, which will enlarge this value up here, which will cause this whole term here to increase, meaning that you need more strength in the member to offset the moment magnification. Again, you have two equations based on the value of the ratio of the axial load to the axial strength. There's an example here to go through quickly. It's a beam column. We've got axial loading and bending, but it's bending only about the weak axis. Here I've picked off all the section properties I think I need. We first look at it as a column. You calculate the effective length of both axes. It's pinned for both axes, meaning that K is equal to 1. So the effective length is equal to the actual length, and the YY axis is going to control. I come in and calculate a KL over RY, because I'll need that later. It comes out to be 105. Calculate by lambda sub CY, which is 105 divided by pi times FY. We're using a 50 grade steel. Modulus is always 29,000. Comes out to be 1.39 or 1.4, which is less than 1.5. So we use the one equation that's actually in it looks like this, but the load, the design load, is the F critical times the gross area times the phi of 0.85, comes out to be about 168 kips. The YY bending strength, or the YY bending due to the loading, again is WL squared over 8, and it was what, 0.5 kips per foot. It's only 9 kip feet, but it's not much. But we don't have much strength in the weak axis. There's no bending in the strong axis, so that goes to 0. The bending strength of the weak axis is based on ZY. Comes out to be, again, watch the units, but 33.2 kip feet. Again, use C sub m equal to 1. That's what it is anyways, but it's conservative. You calculate the Euler buckling load, 229. The B1, and that plugs in here. The actual load on the column is 80 kips. And you come up with a moment magnification factor of 1.54. What that is saying is that the axial load increases the moment further, actually increases it by 54%, which is pretty significant. So you don't want to ignore it on an exam, because you'll end up with a beam that may fail. You calculate the ratio of the axial load to the axial strength. Comes out to be almost 0.5, which is greater than 0.2. And you then use this equation, which is shown here. Note that it doesn't have any strong axis bending term, because there's no bending about the strong axis. Running through the numbers, though, it comes out to be 0.85, which is less than 1, so you're okay. If it was greater than 1, you were in a design situation. You'd have to go back and try a larger section. The problem with all this is that you can't have any tables or that gives you the answer directly. It's an iterative process, and I just hope that they don't give you a problem like that, where you have to select a section because it takes a while. Usually, it's an evaluation problem, like the example here. Okay, looking at methods of connections. How do we connect our tension member into our building? We want to look at fasteners, bolts, and welds. For structural steel design, we have two types of bolts, or actually three. One is unfinished bolts, the A307. More typical, though, are the high-strength bolts of ASTM designation A325 and A490, where the A490 has higher strength than the A325. Unfinished bolt is, again, if you went to Walmart, you probably might get that. Okay, but these are specialty bolts that have to get from a supplier. Not you, but they're not your run-of-the-mill. What's unique about high-strength bolts is they're made out of high-strength steel so they can resist higher loads, but it allows the application of a tightening force that will develop a clamping action in the bolt, meaning you can torque up the nut really tight, putting the bolt into tension without failure. And what that does is actually compress the plates together, and it gives us good behavior in the sense that if we have any type of cyclic loading, we're not going to get movement between the plates. And that's very important, say, if you're doing a design of a bridge, okay, or I don't know, if you on an automobile, on an engine, what do you do when you do the block? Put the headers on a block.
So you don't want them sliding around.
Yeah, you got to torque them up to the proper level. What's happening is you're putting a preload or a tensile force in that bolt to make sure that you don't get any movement there. Any fastener on a car or on a tank is going to be torqued up to a relatively high load to prevent any movement or so that the nut doesn't back off. Okay, load conditions that we have for bolts, they're either in tension, as shown here, or in shear. The strength of a single bolt in tension is given by this formula. Don't worry about it because all the strengths for the various bolt diameters are given in tables. Most of the time, there's very few structural connections load the bolts in tension. They're usually in shear. For high-strength bolts subject to shear, we have several cases that can happen for the two bolt designations that we have. X or N. X means that the threads of the bolt do not lie in the failure plane. What's going to happen is, as the bolt goes to failure, it's going to form a shear plane right at this interface. If the threads aren't in that shear plane, well, then we've got the full area or diameter of the bolt to resist that force. And that, if the threads are excluded from the shear plane, then it's designated as X. If the threads happen to be in the shear plane, well, then we have to use a net area, and it's designated as N. In the actual calculation, we don't actually calculate the strength based on the net area. The allowable shear strength that we're allowed is reduced accordingly. And actually, we don't even do the calculation. We just pick all the values out of tables. In slip critical, it's designated by the SC designation. There, what happens is that we've got the clamping action, and the force is actually transferred through the friction between the plates. Now, a lot of times what will happen is, instead of clamping two plates together, you might do a connection where three plates come together, where a single plate carries the load, and then it gets split out to two side plates. When that happens, you end up at failure developing two shear planes, and that's called double shear. But that actually gives you double the strength in the bolt, okay? Because now you can get two shear forces developing in the bolt to resist the connection force. Okay, so you see these designations, plus you see single shear and double shear, and you'll see that in the tables in a minute. What can affect the strength of a bolted connection is the type of hole we use. It affects the slip critical bolts more than the bearing type bolts. For the standard hole, we don't usually there's no deduction in strength, but the standard hole again can't be oversized by more than that 1/16 of an inch that we assumed. Slip critical, what happens is we can have oversizing, but what that does is take away area of the plate. And that area of the plate was giving us the strength, the resistance in the connection, because that's where the shear, not the shear, but the frictional stresses or forces were developing to resist slippage in the connection.